Just in case you missed it at the end of the last video, there is no video for the subsection called Finding the Domain and Range of Sine and Cosine. That section is very short, so I didn't bother with a video for it. You should still read that section, that subsection, before coming to class, but we'll discuss it in class. Okay, I've given us a nice big unit circle to work with here. It's not really a unit circle yet because I haven't labeled it as having a radius of 1, but I will be doing that. So in fact, why don't we just do that now? We'll say this is a radius of 1. The first angle I'm going to draw in here is the 45-degree angle, or pi over 4. And then I'm going to add the 30-degree angle, just a little bit shy of that. 30 degrees is pi over 6. And then 60 degrees is a little bit more than 45. That's pi over 3. These are important angles in trigonometry. These are going to be the coordinates of the cosine and the sine of those angles. But the angle itself is, here is pi over 6, or 30, here is pi over 4, or 45, and here is pi over 3, or 60 degrees. The other angles that are important are 0 degrees, or radians, and 90 degrees, or pi over 2 radians. I'll go ahead and label that as well. I think I'm going to erase my label here, my y label, so that it's a little bit easier to add the pi over 2. And I'll put 0 down here. These are the most important angles in trigonometry in that they come up a lot. So it's important to be able to work with them. You will, of course, occasionally see a question about the let's say the sine or the cosine of pi over 12, or the sine or the cosine of 0.26 radians, for example, pi sine or the cosine of 12 degrees. Those are not in that sort of nice angle category. They're in familiar angle category. But with these angles, with the angles that are labeled on the screen here, these are the ones we can work out without a calculator, work on without a calculator. And I will expect you to do that for the most part with these angles. Will there be times when it's appropriate to work with a calculator? Yes, of course there will. And we'll talk about that in class. But by and large, what's important is that you can work on these angles without necessarily using a calculator. I don't know if you've noticed, but all 5 of these angles, 0, pi over 6, pi over 4, pi over 3, and pi over 2, are in and around the first quadrant. What if one of our angles is in the second quadrant, or third or fourth quadrant? We could, in fact, find the sine and cosine for, let's see, I'll draw a couple more angles in here. This one right here is halfway between 90 degrees and 180 degrees. So if we give that a label there, it's equivalent to the 45-degree angle here, the pi over 4 angle here, but its measurement is not pi over 4. Its measurement is 90 degrees, or pi over 2, plus another pi over 4, right? This is being, the second quadrant here is being bisected. It's being cut exactly in half by this angle here. So the actual measurement of this angle, we start here on the initial ray in standard position with the initial ray on the positive x-axis, and move in this direction counterclockwise and land here. We will have to go through 90 degrees first, and then an additional 45 degrees. We will have to go through pi over 2 first, and then an additional pi over 4 radians. So we need to figure out what that is, and then we can come back and talk about how to find its sine and cosine. Well, to find out what its measurement is, if I think about it in terms of how many pi over 4s, I could go all the way up to pi over 4. That's 1 pi over 4, one copy of pi over 4. If I go to pi over 2, that's like 2 copies of pi over 4. 2 times pi over 4 is 2 pi over 4, which reduces to pi over 2, right? So while this is pi over 2, the name of this angle in radians is pi over 2. Another way to think of it is as 2 copies of this angle, the angle of the size pi over 4. There's 1 pi over 4. Here's a second pi over 4. Well, here's a third pi over 4. So let's label this one 3 pi over 4. And I could do the same thing in the third quadrant. I bisect the third quadrant, then I have 1 pi over 4, 1 copy, 2 copies of pi over 4, 3 copies of pi over 4. Here's a fourth copy of pi over 4. 4 copies of pi over 4 is just pi. So on my way to finding the angle measure of this one, I've found the angle measure in radians of this one. And this one here, I've got 1 copy, 2 copies, 3 copies, 4 copies, 5 copies of pi over 4. 5 pi over 4. This one here, remembering that this angle, this line segment right here is bisecting the third quadrant. These two angles are the same. So this is the 5th copy of pi over 4. This one's going to be the 6th copy of pi over 4. And 6 pi over 4 reduces to 3 pi over 2. So this is 3 pi over 2. And for quadrant 4, I have something that looks like that. And if I have 1 copy of pi over 4, 2 pi over 4s, 3 pi over 4s, 4 pi over 4s, 5 pi over 4s, 6 pi over 4s, then this must be 7 pi over 4s. 7 pi over 4. And last but not least, this is 8 pi over 4. Well, 8 pi over 4 is just 2 pi. And that's all the way around the circle, so that makes absolute sense. It also helps us remember what it means to be a coterminal angle. The terminal ray for this angle is either 0 radians, or we've gone all the way around, but we've landed in the same place at 2 pi radians. These two angles are coterminal. They land in the same place. They end in the same place. So right now we're only dealing with the pi over 4 angles, the pi over 4, and then kind of all of its relatives, if you will. So we've got this one in the 2nd quadrant, and then in the 3rd and 4th quadrant. And I hope it makes sense to you. Well, let's recall, first of all, that the coordinates of this point here are 1 over the square root of 2, comma, 1 over the square root of 2. 1 over the square root of 2. Okay? And remembering that the way we got those coordinates was to go out and up, right? Out this distance, which we have defined as the cosine of t, cosine of the angle, and then up this distance, which we have defined as the sine of that same angle. Well, we could do the same thing here. We're going to have to go out and up. Here we're going to have to go out and down. This is going to be out and down. Here we're going to have to go left and up, whereas here we went right and up. So if I were just finding the coordinates of this point in terms of x and y, no trigonometry necessary, I would say that they were a negative x and a positive y, in the same way that this has a positive x and a positive y. This one down here is going to have, let's see, where should I put this? A negative x and a negative y, right? Both the x and the y coordinates are negative. And this one here has a positive x, but still has a negative y. And that's just algebra, right? We know that, forget about the circle. We know that to find the coordinates of a point, you have to go out to the right and up if you're in the 1st quadrant. If you're in the 3rd quadrant, say, you're going to go to the left. That's going to be a negative x value. And then you're going to have to go down, which gives you a negative y value. So we have a negative x and a negative y. That's just from algebra. Now, if we look at the coordinates of the point associated with the pi over 4 angle, with the 45-degree angle, we remember that we drew a triangle here, that it was a right triangle, that it was an isosceles triangle. This side length had the same as this side length. Let me put in that dotted line. So hopefully this will help you remember or visualize that it's a kind of a triangle we're looking at here. We had said that the radius of the circle was 1, so therefore the hypotenuse of our triangle is 1. And then we said, well, x and y have the same coordinates here, so that gave us not just x squared plus y squared equals r squared, but x squared plus x squared equals y squared. And we found these coordinates from that process. Well, if we do the same thing over here, we still have a radius of 1, and we still have these two angles being equal. So therefore, these two angles are both 45. We still have the same triangle here. It's just in a different orientation. So the length of this line here, let me use a different color. So the length of this line segment and the length of this line segment are the same. So we can use the same trick, if you will, to figure out what the coordinates are. So the coordinates here are just 1 over the square root of 2, comma, 1 over the square root of 2. Got my square root. The difference is that because of where the point is, we have negative and positive coordinates. The x has to be negative, the y has to be positive. Close my parentheses there, and in fact, I'm going to erase the opening parenthesis because I need a little more room. I need to put my negative in there. So I'll give myself a bit more space. And then this has to be negative. Rather than starting from scratch, trying to figure out what the sine and the cosine are for this angle here, right? We can use the same trick, if you will, to find the coordinates and then just recognize that one of the coordinates has to be negative and make sure it's the right one, right? In quadrant 2, x coordinates are always negative. All the x coordinates in this quadrant are negative, and y is still positive. So here are our coordinates for this, but something important to recognize is that what we've just done is we've described something called a reference angle. This angle right here is not the same as the angle we were actually trying to find. Hang on a second, let me use a different color again here. I was looking for the sine and cosine of this angle. That's my t, that's my theta, right? But what I've done is I've used this angle instead to find that information. And this angle right here, we call that a reference angle. There's another one here and another one here. So the coordinates of this point are also going to be 1 over the square root of 2, 1 over the square root of 2. Keep doing that, forgetting my square root. But because I'm in quadrant 3, both the x and the y coordinates have to be negative, so I need to make sure that I include that. And in quadrant 4, 1 over the square root of 2, comma, 1 over the square root of 2. And I'm in quadrant 4, so my coordinates are x is positive, y is negative. So we'll leave x as it is and add a negative to my y coordinate. So the numerical coordinates are the same for all 4 of these because the reference angle is 45 degrees. Let me put a 45 degrees. I'll put a double mark in there. Okay, so all of these angles that have a 2 mark, a double angle marker, if you will, those are all 45-degree angles. You have to be careful that you recognize that the angle you're looking for is not this angle here. The angle you're looking for the cosine and sine for is this angle, or this angle, or this angle. All right? That's an important distinction to make. But we can use the trick we learned in quadrant 1 and just apply it to quadrant 2. This video is getting a little bit long, so I'm going to stop here, but I want to make the point that we've just done this for 45-degree angles, or pi over 4. We can also do it for pi over 6 and pi over 3, but I'm just going to do it for pi over 6. Notice that the angle that I'm drawing here is closer to the x-axis. So the reference angle is the one that's closest to the x-axis. All right, so this is pi over 6. These all have a reference angle of pi over 6. So my reference angle here is the original pi over 6 for, I'm not sure, I'll use a highlighter, I think, how to explain this one. Pi over 6 is, this is not pi over 6. That is not that angle, but I can use the reference angle for pi over 6 of pi over 6 to figure out what the coordinates for this angle are because the reference angle is pi over 6, right? It's the same stuff, just with different signs. All right, the next section is called using reference angles. So we're going to stop here and we'll talk about the rest of this in that video.